Hi, everyone. Hope everybody's doing well on this Sunday evening. And what could be better than talking about some probability on a Sunday night? I genuinely enjoy talking about probability. And I don't know, I feel like it's a good way to end the week and for you to begin it on Monday. Now, just a couple of brief things I wanted to point out before we get going here. First of all, this week will likely be the last time that we'll have kind of a common thread of material between Prob and Stats and theory of probability. God's providence in this transition into a new normal, there was a lot of overlapped material that enabled me to be able to find a spine through which both classes could work. I did have to post a few extra little tidbits for the theory of probability folks. That's okay. And that's going to happen more and more. I think tomorrow and maybe a little bit of Wednesday will be the last time I'll be able to do that, because in Prob and Stats, it will be exclusively statistics applications at that point. Okay. I don't anticipate what I'm going to talk about taking that long. It seems like it's fairly intuitive stuff, even though it's multi-variables that are involved. But it's just simply an extension of the stuff that we have been doing with one variable. For both these classes, Prob and Stats and Theory of Probability, I think I'm almost caught up completely with grading. So if not by the time you watch this, very soon after, I will be completely caught up. So you should have a very good idea of where you stand in the class. So I would go check that out, just make sure that everything seems like it's in good order. And this week there will be homework quizzes that I will post for each class, and those will likely be due on Friday. Okay, so be looking for those in the days to come here pretty soon. All right, so let's get to it here. All right, so let's see, share this, and we will dive in. Okay, so we've been talking about almost exclusively about one variable, one random variable, and that's it. Now we're going to move into a context in which we'll have multiple variables going on, and we're going to concentrate mostly on the case of two variables, in fact almost exclusively on that. But it turns out all the stuff that we're talking about has analogs in higher numbers of variables as well, 3, 4, 5, what have you. Okay, and once you understand what's going on for two, it's really not all that much of a stretch to actually extend that to any number of variables. Okay, so just keep that in mind. So first of all, we use this term bivariate to mean two variables. If we were in higher number of variables, we would just say multivariate distributions. Okay, so we're going to be looking at the case where we have two random variables, each of which happens to be recording something about some random event that's underlying the situation at hand. It has to be the same random experiment so that we're sampling from the same sample space, and each of the random variables is going to be describing some aspect of that, and we'll ask questions about those random variables. Okay. So first we're going to talk about discrete bivariate distributions, which we know well the difference between discrete and continuous data at this point. Discrete means listable, and continuous means unlistable. Okay? And as you know, in the discrete case, we have lots of things that involve sums, whereas in the continuous case, you have lots of things that involved integrals. The same thing is going to be true here. Okay? So let's take a couple of random variables, x and y, that are discrete. both defined on the same sample space of the same random experiment. We call the PMF, the probability mass function of these two, the joint probability mass function. Incidentally, sometimes you actually say the bivariate probability mass function if you have two variables, but most of the time you just say joint probability mass function, and that could refer to actually any number of variables, okay? So P of X, Y, remember before we had like P of X for just, P of X was the probability that the random variable X was equal to little x. Here we have the P of X, Y, so X, Y is an ordered pair of possible outcomes for the random variable X and the random variable Y, with X, little x corresponding to capital X and little y corresponding to capital Y. Okay, and P of X, Y is just defined to be the probability that X is equal to little x and Y is equal to little y. That's it. Okay, and you define that little bivariate function for every pair of possible outcomes, X comma Y. Okay. Now, what would have to be true about this joint PMF in order for it to be a joint PMF? Well, if I sum over all the, that's what this says, if I sum over all the possible outcome pairs, P of X, Y, I'd better get 1. And of course, all of these things are equal to or greater than 0 for all X and Y, okay? For all outcome pairs X, Y, okay? So pretty straightforward definition here. Okay, and what about like the individual random variables themselves? Well, it turns out we can take the joint PMF and extract just the ordinary PMF for each one. We call those the marginal PMFs. Okay, so marginal, I mean, that just means that you're trying to get rid of one of the variables. If you have a joint PMF for both random variables, the marginal PMF just means you're getting rid of one of the variables. How am I going to do that? Well, okay, and incidentally, now I actually have to put a little sub-index on the PMF so I know which one corresponds to X and which one corresponds to Y. Okay, so P sub capital X of little x, how do I get that? Well, I just add up all the values from the joint PMF over all possible Y values. And of course, what this means is all Y such that P of XY is bigger than 0. Of course, who cares about the Y where P of XY is equal to 0? That's not going to change this sum at all. So I just have to add up all the values. So P sub X of X for a fixed X, I add up all the Y values, and that gives me the probability that capital X is equal to little x, because after all, I've let Y run through all of its possible values for that fixed X. And so I'm going to get the probability that capital X is equal to little x. And similarly for Y, I just add up all the joint PMF values over X's where P of XY is bigger than 0. And we'll do an example here pretty quick, but that's called the marginal probability mass functions, okay, of X and Y. I can extract those from the joint PMF. Okay. Let's do an example. Let X denote the number of hoses being used, and let Y denote the number of hoses in use at that time. Okay. The joint probability math, I mean, look, the setup of the problem is just sort of silly. You don't need to worry too much about that, but the joint probability mass function of X and Y is given by, now it sort of makes sense that, I guess, so X's number of hoses being used, Y is the number of hoses in use at that time. One of those two is going to be smaller than or equal to the other one, okay? But that's just kind of an interesting feature of the setup here. But what really matters is the joint PMF, and here's the table for that. So I have X values labeled down the left and Y values labeled in columns. So X in rows, Y in columns. Okay. So what this is saying is like P00 is equal to 0.10. P0, if X is 0 and Y is 1, the probability of that happening is 0.04, etc. of course, what should happen if I add all this stuff together? I should get 1, okay? So they want me to compute the probability that x is equal to or less than 1 and y is equal to or less than 1. And they want me to compute the marginal probability mass function of x and y, okay? So, and then it says, hey, using the marginal PMF for x, what is the probability that x is equal to or less than 1? Okay, so let's just kind of work through that one. Okay, so let me stop sharing that and we'll move over into the other venue here. Okay, so here we are. And obviously my kids have been messing around with my iPad. I got an Apple Pen recently, and so they were excited to make good use out of that. Okay, but nonetheless, oh, here's a pretty cool one right here. Check that out. Enjoy that. Okay, so let's do another page here so we can get going. All right, so just to kind of, you know, I'll copy down this thing here. Okay, this is a purple pen, which is kind of interesting. Okay, so there's 0, 1, and 2. These are the values for the probability, the joint probability mass function, P of x, y. Okay, and I have x going down the rows here, 0, 1, and 2. I have 0.1, 0.04. I have 0.02, 0.08, 0.20, and 0.06, and 0.06, and 0.14, and 0.30. Okay. I gotta be honest with you, I'm not a purple pen guy, all right? So I'm gonna get rid of that, okay? So what we were asked to do in this problem was to compute the probability that x is equal to or less than 1 and that y is equal to or less than 1. Well, okay, so that's going to be, if you think about it, that's going to be p0, 0 plus p, okay, 0, 1 plus p1, 0, right? That's another ordered pair that satisfies both x and y equal to or less than 1, plus p1, 1. Okay, so really what we did here is we kind of looked at all these things which happen to be sitting right there, okay? So what do we get here? You just add those things together, right? This is 0.10, I mean, just so you don't get confused here, it's 0.10 and 0.20, okay? So that's gonna be 0.14 plus 0.08 is 0.22, so like 0.40, 0.42, okay? The other thing they asked us to do was to compute the marginal probability mass function of x, the marginal probability mass function of x. So the marginal PMF, okay? P sub x of little x, okay? So, okay, how are we gonna get that? Well, what we do is we say, all right, so what is P sub x of 0? Well, that means, how in the world am I gonna get that? Well, if I want zeros, let me kind of, I will use a different color here. I'll go with red, okay? That means I'm gonna look right here, okay? I look at all possible things that are happening when x happens to be equal to 0. And I add all of these things together that happen to be in this row, okay? So what do I get? It's gonna be P0, 0 plus P01 plus P02, okay, which apparently is what? 0.16, okay? All right, so what about, let me go back to my black here. What about Px of 1? So that's Px of 0. Let's just do So let me just say Px of 0 is 0.16. Okay, what's P sub x of 1? Well, that's going to come from adding up everything in the 1 row right here, okay, and putting that right there. So this guy gave rise to this. Px of 1, okay, that's going to be 0.28, 0.08 plus 0.20 is 0.28 plus 0.06, so it's 0.34. Okay, and then finally, Px, P sub x of 2, what's up with that? Okay, so P sub x of 2. This will complete our exploration of the marginal PMF. What do we get? Well, if you look at the first two things, you kind of know what this is going to have to be. Okay, P sub x of 0 and P sub x of 1 add up to give you 50%. Therefore, this thing would have to be 0.5. Is it? Yes, it is. There it is. Okay. And the last question they asked us was, what is the probability that x is equal to or less than 1? Okay, well, that just is going to be, that's going to be gotten at by adding these two things together, right? So that's going to be 0.50. 0.50. Okay, there you go. Okay, so that said, we're ready to move. Okay, so let's talk about independence a little bit here. Okay, so we've talked about independence in the sense of events, but here what we're talking about is independence in the sense of random variables themselves. Okay, so when we do that, what we mean is that the events that are determined by the random variables x and y are independent. Okay, so that is any event that I might have happening because of the random variable x and the random variable y, those events themselves will be independent. Okay, so what does that mean down on the level of the probability mass functions? Well, you know, if every event determined by x and determined by y, if those events are independent, then it stands to reason that like individual probabilities that we get from the probability mass function would satisfy that relationship we had for events. Remember, like the probability of A intersected with B was equal to the probability of A times the probability of B. That was one of the features or one of the ways we could talk about independence of events. So a similar thing happens in the case of the PMFs. Okay, so independence can be characterized for a pair of random variables in that the joint PMF is equal to the product of the marginals at that ordered pair XY. So P of XY is equal to the marginal of X at X times the marginal PMF of Y at Y. Okay, that's the meaning of independence for random variables. That gets at exactly what I said, namely that any event determined by X and any event determined by Y, those events are going to be independent. That's what independence means in the case of random variables. And if that condition is not met, and that is captured by this little PMF identity right here, then they are not independent. They are dependent. Okay? And moving a little bit deeper, if I had a bunch of random variables, n of them, say, they're said to be mutually independent if every subset of any size, whether it be pairs, triples, what have you, k-tuples, whatever, the joint probability mass function or probability density function of the subset is equal, sorry, there's some typos in here, is equal to the product of the marginal probability mass functions or probability density functions. Sorry, there's a couple of typos right there. So the density function of the subset is equal to the product of the marginal probability mass functions, or probability density functions. But the main thing I want you to be aware of is the case of 2 right here. Essentially, all I'm saying is any joint probability distribution has to be equal to the product of the marginals. That's how you know a bunch of random variables are independent. Okay, that relationship always has to be satisfied. Okay, are the x and the y independent from back in that previous example right there? Okay, is p of xy equal to the product of p of x? Is it equal to the product of the marginals for any pair x and y? Okay, is that true? Well, I don't know. Let's kind of check that out here. So let's take a peek back at this thing, and we'll sort that out. Okay, so here we are back in this good old thing. I erased some stuff that was unessential to this discussion, but the question was whether the random variables x and y described in this this joint PMF table are actually independent. Well, we have the marginal for x, but let's get the marginal for y as well. Okay, so what about p sub y? Okay, what about p sub y? Oops. P sub y of 0. Well, how am I going to get that? Well, let me just circle this right here. Okay, so I have to, for the value 0 in the column, I have to add up all these things. Now I'm going to get this. Yeah. Okay, so I have to add those things together. What do we get? Well, that's about 0.24. 0.24. Okay, what about p sub y of 1? Well, I add up everything in the 1 column here, okay, which are these guys right here. Okay, so what do we get? Well, we get 0.34, 0.38. Okay, and just to check ourselves, we should add these together. That's 0.62 total. So we'd expect to get 0.38 for the last thing, and indeed that is the case. Okay, so 0.38 is what we get here. 0.38. Okay, so over here we have the joint PMF for x, or we have the marginal PMF for x. We have the marginal PMF for y. So let's start looking at, let's make a table of some of these values. Like p00, of course, is equal to 0.10. Okay, so what is p sub x of 0 and p sub y of 0? What do I get if I multiply those together? Well, it's 0.24 or 0.16 times 0.24. Okay, and if you plug that in, I get 0.0384. 0.0384. By the way, which is not equal to p of 0, 0. Okay, and the minute that we find one case where the joint distribution function, the joint PMF, is not equal to the product of the marginals, that's it. They are not independent. So x and y are dependent. Okay, dependent in this particular case. So there you have it. So are x and y independent? No, they are not. Okay, so there you go. So let's talk about like what you would do if you had some weird function of the random variables x and y. We've seen this kind of thing before. So you have the joint probability mass function. By the way, we'll just kind of drop the word joint because that's helpful kind of at the beginning here, but eventually it's like obvious that it's a joint PMF because you have multiple variables floating around. But a lot of times we still keep the word marginal for the individual PMFs for the individual random variables, just so that we have an adjective to describe those and distinguish them from the joint probability mass function. Okay, but we have the probability mass function P of xy, probability density function f of xy, or that should actually be P of xy. Sorry guys, I'm making a couple of typos here. The expected value of a function of the random variables, capital X, capital Y, denoted by the expected value of h of x comma y. By the way, that could be like the product of x and y. Could be like x squared times y minus y squared times, you know, x squared or something. It could be any weird function of the random variables x and y. Oftentimes that's denoted by mu sub h of xy. Okay, and what you do is you just add up over all possible outcome pairs xy, h of little x little y times the probability mass function, the joint probability mass function. There it is. Okay, by the way, this is a third typo that I've noticed so far in the first 9 slides. Sorry about that. I'll definitely fix that and repost. I beg your forgiveness on those. Okay, so here's another one. An instructor has given a quiz with 2 parts. For a randomly selected student, let X be the number of points earned on the first part and Y be the number of points earned on the second part. The joint probability mass function is given below. Okay. There we go. And now some problems on that. I'll go ahead and copy that down on the whiteboard and we'll work with that. And here are the problems they want us to do. If the score recorded in the grade book is the total number of points earned on the 2 parts, what is the expected recorded score? And then various things after that. Wants us to compute various things about this joint PMF. Okay, so let's go ahead and do that. Okay, so let's have a look at this. I've copied down the PMF right here for the joint PMF for these 2 random variables. And just to remind you, X is the number on part 1 of the quiz. Y is the number of points on part 2 of the quiz. Apparently, you can get 0 or 5 or 10 or 15 points on part 2, and you can get 0 or 5 or 10 on part 1, apparently. And letter A that they wanted us to determine was they said if the score recorded in the grade book is the total number of points earned, okay, the total number of points earned, then what is the expected recorded score? Okay, the total number of points earned is going to be what? Well, X plus Y. So they said the expected recorded score. So that means they want the expected value of X plus Y. Okay, they want the expected value of X plus Y. Okay, so like what is that going to be? Well, what you're going to do is you're going to take the actual values that X plus Y could take on. So for instance, 0 plus 0. Okay, so what is that going to be multiplied by? Well, P of 0, 0, obviously, okay? And then, you know, if X is 0 and Y is 5, okay, that's going to be P of 0, 5. Okay, and then let's see, let's just add some other ones in here. So like 0 plus 10. So what I'm saying there is X was 0 and Y was 10. That's going to be P 0, X was 0 and Y was 10, plus 0 plus 15. P of 0, 15. And I think you kind of see how this is going to go. So I am going to pause this and kind of complete this thing for us, and then we'll move on to the next thing. All right, we're back in here. Okay, so I basically got 14.1 for the expected recorded score if the recorded score is the sum of the two things. Okay, again, these probabilities are the probabilities of various X and Y scores on this thing. Okay, one thing that I will point out here is the following. If you think about it for a minute, when is the sum, first of all, 0 doesn't contribute anything to this. 0 plus 0, I mean, that's going to just kill that probability. Okay, one thing you could do is you could say, okay, well, if the recorded score is 5, if we're doing X plus Y, that would just be the sum of these two entries, right? So this would be a score of 5, right? So this would be a score equal to 5, okay? Which is why you see this thing right here, okay? That's where that came from, okay? Basically 5 times 0.10. What about a score of 10? Well, that's really any of these things right here. So that's a score of 10, which gives rise to this, okay? If I add those probabilities together, I get 0.18, okay? Similarly, a recorded score of 15 comes from that diagonal, okay, and that gives rise to this thing right here. You think about it for a minute, okay, and so on and so forth, right? So this guy right here corresponds to the, the 20, a score of 20, that happens with 24% probability, okay? And then this thing right here, of course, that corresponds to that guy, okay? And you get 14.1. Now the next problem, I'm not going to go through it in any kind of detail, but the next problem was, what if the recorded score was the maximum of the two scores? Now that's still a function of X and Y. Okay, you would have to just take the maximum value of X and Y, okay, and record that instead and multiply by the probability that XY occurs, okay? So I won't go through that in any kind of detail, but I want to focus on this other one. What is the standard deviation of X? The standard deviation of X, okay? So I want to erase all this nonsense that I have going on down here. Okay, so make myself a little bit of room here. Okay, so the standard deviation of X, well, that is going to require that I actually know what the probability mass function is for this thing, is it not? Yeah, because, I'm going to need to know what the expected value and what the expectation of X squared is. In fact, I may even want to get the moment generating function for this thing. Maybe that would kind of be the way to go. And one thing I wanted to point out is the following. Oops, let me change my pen color here. Okay, so look, I can actually draw a little end result here for this table. Okay, so look, if I want to get P sub X, the marginal probability mass function for X, that means I need to add across this row right here, okay? And if I add across this row, because I have to add across all the Y values, I get P sub X of 0, okay? Which is what? Well, it's going to be 0.20, okay? What about P sub X of 1? Well, P sub X of 1 is I'm just going to add across this row right here. Actually, this is 5. Excuse me, it's 5. So what am I going to get here? It's going to be 0.3 plus 0.15 is 0.45, 0.49. And I always just kind of like to check myself on the last one here. What about, okay, so let's see here. So far I have 0.69, which means I should have 0.31 in this last row. Is that true? So P sub X of 10. Okay, so what is that? Is it 0.31? Well, let's see, 0.29, 0.30, 0.31. Yep. Okay. You notice if you add everything together here, I get 1. Okay. And of course, if I wanted the probability, if I wanted the marginal density for Y, you can kind of see how I would get that here, right? So I would have, you know, for 1 or for 0, I would have 0.07. For 5, look, I mean, you don't have to write, like over here I wrote P sub X of 0 equals 0.20, but it's just understood that that corresponds to the 0, right? It corresponds to this entry right here. Okay, so you kind of know that that row is going to be the marginal evaluated at 0. Okay, so what about this one? I mean, this is just for practice. This is 0.36. The next one, what is that? That's also 0.36, it looks like. Okay, and the last one is 0.21. These add together, let's see here, 0.72, 0.79. Yes, that adds up to 1. So that's kind of nice. But they wanted to know what the standard deviation of X was. Okay, what is the standard deviation of X? Well, let's figure out what the moment generating function of X is. Okay, it's going to have 3 summands. It's going to be 0.20 plus, right? So it would be 0.20 e to the 0t plus 0.49 e to the 5t, right? Plus, okay, because x was 5 for that one, plus 0.31 e to the 10t. Yes? Okay. So what would I have to do here to figure out what the standard deviation was? Well, I would have to take the derivative of this. Okay, so like mx prime of t equals, okay, the constant term goes away, okay, and then I would have 5 times 0.49, okay, because of the chain rule. Okay, so that would be 2.45 e to the 5t plus, okay, 10 times 0.31 is 3.1 e to the 10t, okay? So there's the first derivative, okay? And let me just see here. I need another screen to deal with here. Okay, so 2.45 e to the 5t, 3.1 e to the 10t. So 2.45 e to the 5t plus 3.1 e to the 10t. That's what mx prime of t was equal to. Okay, so what about the second derivative here? Well, okay, so then I would have to multiply 2.45 by 5 again. I get 12.25 e to the 5t plus, okay, and that one's easy. It's just 31 e to the 10t. Okay, so the variance of x is equal to what? Okay, we're pretty comfortable with this sort of thing at this point, hopefully. So it's going to be mx double prime evaluated at 0 minus mx prime of 0 squared. Okay, so what would I get here? Well, if I evaluate the second derivative at 0, okay, if I evaluate the second derivative at 0, what do I get? Well, it's going to be 43.25 minus, okay, a first derivative evaluated at 0, okay, and then I have to square that, so that's going to be 2.45 plus 3.1, which is equal to that, and I have to square that, okay. Okay, so it's 5.55, and then I have to square that, okay, so 30.8025. Okay, so 43.25 minus the answer here. Okay, so it's 12.4475. Okay, so there we have it. There we have it. Okay, and there was another question here at the bottom that I wanna come back to here in just a second. Okay, they did want us to find the standard deviation of this. Okay, and the standard deviation, of course, is just gonna be the square root of the variance of this thing. But there was a last question here that I want us to look at, namely, they said, are the random variables independent? Are the random variables in question independent? Well, let's go back to the previous screen and take a look at that, okay? So are they? I don't know. Let's take a little peek at this, okay? So first of all, I don't really think I need all of this other junk anymore. So let's erase all of this, okay? Just to give ourselves a little room here on the bottom of the old screen to help us out. Okay, so what about it? Let's see. Well, let's just look at, for instance, P00. Okay, so what about P00? Well, that's 0.02. And on the other hand, what is Px of 0? Okay, and Py of 0? Because we should just multiply those together and make sure that this works out. It's always a good place to just try one and see what happens. Okay, so Px of 0 was 0.20, okay? And Py of 0 is 0.07. Okay, so what does that equal to? Okay, 0.07 times 0.20 ends up being 0.014. Uh-oh. That does not equal to 0.02. That's what P00 is. So what does that tell us about X and Y? Okay, so that means that X and Y are dependent. But even like based on the context itself, that kind of makes sense because it seems like that low scores on the first part of the quiz would kind of correspond with low scores on the second part, for instance. So these two things seem like they would they would strongly influence each other, and we know that that doesn't necessarily entail independence, but it does make sense that there's influence going on here, and hence the danger of destroying independence. And in fact, that is what happened. Okay. The last thing that they actually asked us for that I think is worthwhile looking at is the following. What about the expected value of X, Y, the product of X and Y? Now, it turns out that this is a pretty important quantity. Looking at the expected value of the product of two random variables turns out to come up quite a bit in applications. Okay, so and what I would say here is the following. Okay, so let me use the purple color here. That'll make my kids happy. Okay, so I'll make that a little bit bigger. Look, if I look at the product, a bunch of stuff is going to be 0. Like so like I'm going to be doing like 0 times 0, 0 times 5, 0 times 10, 0 times 15, and those are going to have various probabilities weighted on them. So really the only ones that are going to end up surviving are these things right here when you think about it for a second. Okay, so those ones that I've kind of highlighted in purple, right, or kind of boxed out in purple, are the ones that are going to really contribute to the overall value of this. Okay, so let's see here, what's going to happen? So this is equal to, okay, so if I stare at this entry right here, which corresponds to 5, 5, if I look at that entry right there, which happens with 0.15 probability, that's going to be a value of 5 times 5, right? Because X is 5 and Y is 5, which is 25. Okay, so 25 happens with probability 0.15 plus, okay, what about 5 times 10? Well, that's 5 times 10 is 50. And that happens with probability 0.20. Okay, and then I have 5 times 15, which is 75. Okay, And that happens with probability 0.10. I just went across the first row there of things that contribute. And then what do I have? Plus, okay, 10 times 5 is 50 times 0.15 plus, what's the next one? Okay, so it's going to be 10 times 10, which is 100. That happens with probability 0.14 plus, okay, 10 times 15, which is 150. And that happens with probability 0.01. Okay, so I will compute that and I'll be right back. Okay, so if you do the calculation, you get 44.25 for the expected product of the scores. Okay, again, the reason I ignored the first column and the first row is because one of the numbers in those products was 0 and would kill those ones off. Okay, so all that mattered was the other one. So you get an expected product of the first and second part scores being 44.25 when we weight those by their respective probabilities. Okay, so I'm going to make myself a little bit of room here because there was one more question that we wanted to deal with. Okay, so let me erase this. We already determined that X and Y were actually dependent things, but I'm going to erase these things. Okay, the last thing that they wanted us to deal with was whether or not the expected value of the product of X and Y was equal to the product of the expected values of X and Y. Okay, so what is the expected value of X? Well, okay, so I have the marginal distribution right over here, right? So I have the marginal distribution sitting right there. So I can actually compute the expected value of X rather easily. Of course, the 0 isn't going to contribute anything. Okay, what about the 5? So that's going to be 5 times, or let me just go 5 times 0.49, okay, plus, okay, 10 times 0.31. Again, I don't record the 0 because that's not gonna contribute anything anyways. So what does this equal? Okay, 5 times 0.49 plus 10 times 31. Okay, 5 times 0.49 plus 10 times 0.31 equals 5.55. 5.55. Okay, and what about the expected value of Y? Okay, well, again, I have the marginal distribution for Y. That is sitting right here. Okay, right down here. Okay, again, 0 isn't going to contribute anything. Okay, and so I'm going to have 5 times 0.36 plus 10 times 0.36 plus, okay, 15 times 0.21. And what does that end up being? Well, okay, so I get 8.55. Okay, and notice what happens if I take 8.55. Okay, if I take 8.55 and I multiply it by 5.55. Well, let's see. So 8.55 times, so 8.55 times 5.55. What do I get? 47.4525. Okay, so let me just say the expected value of X times the expected value of Y equals, if I multiply those together, I get 47.4525, which is not equal to this. So we don't ever assume necessarily that the expected value of the product of X and Y is equal to the product of the expected values. Okay. In fact, we'll see in just a minute when we know for sure that that will happen. Okay. So Okay, so we've basically answered all of these questions. The last one, we discovered that the expected value of the product is not equal to the product of the expected values of each individual thing. And we found out that the random variables themselves were dependent, okay? So one question that might spring to mind is, hey, when can we know for sure that the expected value of the product is the product of the expected values? And lo and behold, when might you think that would happen? Well, if X and Y are independent, then it's guaranteed that the expected value of the product is equal to the product of the expected values. Now, I will say, though, that just because that happens with expected values, like the expected value of the product of X and Y is equal to the product of the expected values, that does not guarantee independence. Okay? You have to go all the way down to the level of the PMF itself. The joint PMF at any point, X comma Y, has to be equal to the product of the marginals. Has to go all the way down to that. The expected value isn't refined enough. Again, it's a single number summary, whereas the PMF is a whole collection of data. And to have flat out independence for a pair of random variables, you need to go down to the level of the PMF. You have to go down to the level of the PMF. Okay, so no horsing around there. Okay, so if you have any functions h of x and g of y, those should be capitalized. So sorry, another little typo there. And the expected value, okay, so like if x and y are independent, then the expected value of the product of those functions, h of capital X and g of capital Y, is going to be equal to the product of the expected values. So independence implies that you can separate out those products, but just because that product happens for the expected value does not imply that X and Y are independent. That's a big deal. Don't forget it, okay? I want to talk about something called the correlation coefficient. In the theory of probability text, this doesn't actually come up until chapter 7 or so, because it's more in the realm of statistics applications. But it's a really important concept, practically speaking, because people really kind of abuse the concept of correlation and what it actually means. So I want to make sure that every student that's taken any kind of probability course with me for sure understands what's happening with correlation. So a key concept that comes up is something called the covariance between two random variables. Okay, this really is at the essence of what the correlation coefficient means. And it literally, when I say the correlation coefficient, I mean correlation in the sense that people usually talk about. They say, oh, well, those two things are correlated to each other. Well, this is rigorously defining what that means precisely from the perspective of probability and statistics, okay? So the covariance is defined this way. You take the expected value, okay? First of all, you need to know what the mean of X is. That's what that mu sub X is. And you need to know what the mean of Y is. That's what mu sub Y is. And in the covariance of XY is the expected value of X minus mu sub X quantity times the quantity Y minus mu sub Y, okay? And by the way, if you multiply all that out and you push the expectations through, just like we did in the case of variance, it turns out that the thing will simplify and you'll end up with the expected value of XY. There it is. That's why I was kind of making a big deal about computing that in the last example. The expected value of XY minus the expected value of X times the expected value of Y. Now let me point this out, but it's going to come up again in about another slide. If X and Y are independent, then the expected value of XY will be equal to that product of expected values. So what will the covariance be? It will be 0, okay? So again, once again, we have a way to detect if two random variables are not independent, Okay, so that is, if the covariance is anything other than 0, then you know you can't have independence. But on the other hand, if this thing is 0, we don't guarantee, we can't know that the random variables are independent. But if x and y are independent, we know that the covariance will be 0. So if the covariance, if the covariance of x and y is positive, then x and y have a positive linear relationship. Okay, a roughly positive linear relationship. You say that with certainty. Okay, if the covariance of x and y is negative, then x and y have a negative linear relationship. Why? Why would that be true? Well, think about it. I'm basically taking the product of x minus its mean and y minus its mean. If on average that product is positive, that means that that means that whenever x is above its mean, so that this is positive, okay, then this is tending to be above its mean also. Okay, this is tending to be above its mean also. Okay, so if this is positive, then this is tending to be positive. And on the flip side, if x is below its mean, so that this difference is negative, then y is going to do the same thing on average. Y is on average going to be below its mean also, so that we'll have a negative times a negative, which will be positive. So that overall, most of these products, x minus its mean and y minus its mean, most of these products are positive. That's what the average being positive would mean. Okay, but we're only comparing x against its mean and y against its mean. So essentially what's happening here is we're only measuring some kind of linear relationship, nothing more than that. Okay, so if the covariance is positive, then x and y tend to have a positive linear relationship, whereas if the covariance is negative, and by the way, what that means, the covariance is negative, that means this average is negative, which means if y is above the mean, then which means that x minus mu is positive, then y minus mu is going to tend to be negative, which means y will be below its mean. Okay, so here they have kind of a flipped relationship, whereas before, if the covariance was positive, they were both like simultaneously tending to be on the same side of the mean. If the covariance is negative, they're tending to be on opposite sides of their respective means. Okay, but there's still a relationship going on. If the one goes up, the other goes down, and vice versa. Okay, so there you have a negative linear relationship. That is, if x gets big, y gets small. If x gets small, y gets big. Okay. Whereas if it's a positive thing, then if x gets big, y gets big. They're both above their means. Okay. And if x gets small, y gets small. They have a positive linear relationship. Okay. But the covariance is only measuring a linear relationship between x and y. Okay, the so-called correlation coefficient of x and y, denoted by, core of xy, or this is the Greek letter rho of xy, or rho, is just defined by taking the covariance and dividing by the product of the standard deviations of x and y. Okay, and what that's doing is it's kind of normalizing stuff. So like think about the units of the covariance. Okay, if like x is in dollars and y is in dollars also, then the product of these two things, or like on the last example, we had x was points and so was y. Then if I multiply, and if I subtract the mean, that doesn't change the units. It's still going to be points and points. But if I multiply these together, I get points squared as the units for the covariance. That's kind of weird. Okay, points squared as the units. Okay, which is kind of strange. So like here, I would have points squared as the units for the covariance, but points would be the units for the standard deviation for each of these. So points here and points here, so points squared would be the units. So what this does is it gets rid of the units. It just gets rid of the dependency on units for this thing. It kind of standardizes, the covariance and gets rid of the units. Otherwise, the covariance being really big wouldn't mean much. It would just mean that the units, because that would be dependent on the units themselves. Okay, so here we kind of normalize this thing. And by the way, notice what would happen if I took y equal to x. Well, if y was actually equal to x, this would just be, I mean, look at this. It would be expected value of x squared minus expected value of x, or the square of the expected value of x. So if y is equal to x, that's just the formula for the variance. Okay, so the covariance is really a generalization of the variance, okay, where I might have two random variables rather than just one. The covariance of x comma x is just the variance. Okay, so that's a little tidbit to take to the bank there. Okay. But here's this correlation coefficient. And again, of course, the standard deviations are always going to be positive. Dividing by the product of the standard deviation is going to get rid of the units entirely so that this is a standardized quantity, kind of like what we did for the normal distribution when we converted to z-scores. That completely got rid of the units. Okay, we standardized this thing, and it turns out you can show this. I'm not going to prove it, but the rho sub xy, the correlation coefficient, is always between -1 and 1. Okay, of course, it's 0 if the covariance is 0. Okay, but it turns out it's also, you know, if the covariance was positive, then of course rho sub xy is positive, but it can never be more than 1, and it can be never be less than -1. So a positive linear relationship would mean that rho sub xy is positive. A negative linear relationship would mean that rho sub xy is negative. Okay, perfect positive correlation would be if rho sub xy is all the way equal to 1. And perfect negative correlation would be if rho sub xy is equal to -1. Okay. So here's a couple of tidbits that I'll kind of finish with, and we'll come back next time and do an example with some of this and move on to some other things. Covariance depends on the units of measurements. I already kind of said this, but so a larger variance does not necessarily mean that the variables are related more strongly. Correlation is a standardized version of covariance. Okay, so correlation standardizes it by dividing by the standard deviation to get rid of units. The larger the correlation, the stronger the linear relationship between the variables. So perfect correlation would be at the extremes 1 and -1. Okay, and +1 would be positive linear relationship. So if x gets big, y gets big along in a line shape. Okay, perfect negative correlation would be rho sub xy equal to -1, and you would have a perfect negative slope line in that case. Okay, relating x and y. If two variables x and y are independent, then the covariance is 0, and therefore the correlation is also 0, since the correlation actually has the covariance upstairs. And by the way, sometimes you just suppress the word coefficient here, and you just say correlation. Okay. Okay. Of course, if x and y are independent, then you know the expected value of xy is equal to the product of the expected values of x and the expected value of y. And therefore, back here in this formula right here, this would be 0. And so the covariance would be 0. Therefore, the correlation would be 0. Okay. But on the other hand, just because the covariance is 0, that does not guarantee, and hence the correlation coefficient is 0, that does not guarantee independence of x and y. Once again, you would have to go all the way down to the probability mass function level and check that the probability, joint probability mass function of any outcome pair xy was equal to the product of the respective marginals to have independence there. Okay, I think that's all I'm going to do right now. We'll come back and do an example using the correlation coefficient next time, and maybe I'll show you a specific example where the expected value of xy is equal to the expected value of x times the expected value of y, and yet the random variables are clearly dependent. Okay, so that would be a helpful example. I'll do that next time. But that's all I have for now.